All right, introduction to integration by parts. There's some great stuff involved, and of course, I guess Stand and Deliver last year, they kind of got you into the idea that there's this tic-tac-toe thing going. If you watch the movie, and you'll see this clip down here, a little piece of it. So in class I showed, if you guys were here, I'll show you that clip. But the idea is that there is kind of a type of equation. This integral looks fancy on the board. Gets really frustrated, this guy in the video, because he does it the wrong way, or he went backward. We'll talk a little bit about that. But ultimately, what we do for integration by parts, it's a way of breaking down a particular integral into its product parts. And what it is, because it's a product, you can imagine it has something to do with kind of the reverse of the product rule. So here's how this goes. If I actually do the derivative of u times v, like you know in love, because I know you've got this part down, you get u prime v plus v prime u. Now, if I use differential notation and introduce something new, I'm going to change the name of u prime to du and v prime to du, or I'm sorry, dv. So the d means derivative of, and that might help you get the idea of what this differential notation is like. It really does mean the derivative of a particular variable. So if I do that, this is the expression. Now I'm going to undo this. So I took the derivative, here it is. Now I'm going to integrate it like I'm undoing it, going backward. And you realize you kind of get back to an equivalent expression for u times v, but it writes it in a different form that is useful. It introduces a way of breaking up a known integral. So take a look at this. So take the derivative. Now integrate both sides again, basically undoing what I just did. And here's what happened. So the integral of d dx of uv, the d dx, the derivative, cancels with the integral. Kind of fundamental theorem, basic ideas. You have u times v. And then you have integral v du and integral u dv. Cool. Well, this is like the heart and soul of integration by parts. If you understand what happened just there, the rest is just algebra rewriting this. What we're going to do is take that u dv piece on the right-hand side. We're actually going to solve for that, the integral of u dv, because that gives us an integral. We can break up any product integral into a u part and a dv part. And so what I'm interested in is what does that equal to if I use this little expression to rewrite it. So here it is, u dv, that part, is equal to uv minus the integral of v du. That's just an algebraic manipulation of the top equation there. And that, by the way, is our integration by parts. That's the expression we use and take to some of the tougher stuff we do later. We pick a u, we pick a dv, and then we break it up by the rule uv minus integral v du. Pretty fun. So the next piece is, all right, this is this backward Zorro. There's this goofball I saw that used this, and I like this guy, but he likes to use the backward Zorro method. How he organizes it anyway, he thinks of that way. If you can tackle that and kind of latch onto it as your own, great. I tend to just remember the uv minus integral v du is the only thing I need to remember, but you can work any way you like. I'm going to pick a u. I'm just going to go with x, and dv is cosine of x. So you can kind of see dx. And by the way, there's a cosine of x dx. I left off the dx. It should be there. Your dv is always going to pick up that dx. So if you, I'll put it back here in a second. Just give me a moment. Then what I need, so the idea is I just busted up the u dv integral, my original, into a u part and a dv part. With the u part, I'm going to take the derivative of that and get du, which in this case would be 1 dx. I didn't write the 1 in there, but I could if I needed to. And the dv is cosine of x dx. Again, I'm missing the dx, but if I put it back in there, take an antiderivative of it, I get sine of x. So picking a u, picking a dv, u is some part of the product in your integral. The dv is everything else, including the dx. Then you take the derivative of u to get du, which in this case is 1 dx, and you take the antiderivative of your dv to get v. Now you have all the components to fill in the uv minus the integral of v du that is needed in integration by parts. So we're going to put those back in their place, so watch carefully. The Zorro piece is, you can put this whole expression can be described as the uv is the cosine of x dx and x. So the first slash to the left, the backward z in Zorro, is the cosine of x dx times x. That's our original function. The second, the downward slash, that product, the u times the v, that's x sine of x. That's the first part of the integration by part rule. And then the last slash to the left is sine of x times dx, which is the integral of v du that finishes off. But if you need that to remember it, great. But those are the things you put together. left slash for the original, slanted slash for the UV, and backslash for the VDU, and you've got yourself backwards Zorro. So the integral of x, the original, is equal to x sine x minus the integral of sine of x dx. If I put uv back in, that's sine of x and x, minus the integral of v, our sine of x, and du is dx. This is a pretty slick one. Now you notice I can do this. I've got this down. All I have to do is find the integral of sine of x, and I'm home free, which we know. X sine of x equals the, well, sine of x is negative sine, or negative cosine, but we just make negative negative a positive. There it is. We've done it. Integrated the product of x cosine of x dx. All right, let's roll. Now, all I basically is just getting that pattern down, u times v, the original, uv, du, all the components. You pick your u and dv, and then you derive and integrate respectively, filling in the rule after that. Now let's take the derivative of what we got. So see, if we take the derivative of what we got, it should work out. Let's see if it happens. Derivative of x sine x is a product rule. So that's 1 sine x plus x cosine of x. The derivative of x is 1. Sine x stays plus the derivative of sine is cosine times x, the original. Nice little product rule. And then the derivative of cosine is negative sine. And we'll notice the sine of x is cancel, and we got ourselves x cosine x. That's what we started with. So if you can take the derivative of your result and get your integrand, you are home free. And it should work if you've done your work correctly. What about the other way? We picked u to be x and dv to be cosine of x. So could we have swapped those? Would it have worked? Worth a shot. Now I'm going to work through this quickly-ish. Make sure you pause, go back, scan as you need to. Do a little Zorro action there. Okay, do you want to see... If you need any explanation, you just let me know. But there's u cosine of x. dv is everything else and the dx, so x dx. Derive the u, integrate the dv. Now you put it back together, uv. So we got the original equals u times v. That's the 1/2 x squared cosine of x. Integral of v du. Again, 1/2 x squared, and du has got that negative sine of x dx. I changed it instead of... I just pulled the negative out front, so I made it positive in the integral. And then if you look at that, that's kind of a mess. I don't know what to do with that 1/2 x squared sine of x. I started with an x cosine of x. Now I'm up to x squared. That's a big red flag. You just increase the power, which means you increase the complexity of this problem. You took it from an x to an x squared. So if it bumps up the power and complication of the problem, you probably mixed up your u and dv. You probably should turn them around and go the other direction. Now there's an acronym and a shortcut to knowing which to choose as your u and what not to choose as your u, and we'll get to that. But right now you're seeing that if you choose the wrong one, it's not the end of the world, but you'll notice it gets more complicated rather than more doable, something that you can actually integrate. All right, you can read the rest on how to, kind of a regurgitation of what I showed you in the beginning, where the integration of parts comes from. If you read that, you'll get a broader perspective. I'm going to look at this next one, and I'm going to pull the two out first. You might want to do that as well, or not. It doesn't matter. And what you'll do is integrate that thing. So, I'm sorry, you pick your u as x, and dv is e to the 4x. I just picked x to go as u, and dv as the other, just to kind of give you something to start with. Anti-derived necessarily, derived and anti-derived as needed. And then here's my original. Oh, by the way, I wanted to give you a reminder of what it means to take the antiderivative of e to the u if u is linear. It's 1 over u prime e to the u. That's something you want to have down. So here's my uv minus the integral of v du. And this particular version of it, oh, it looks like it got a lot of kind of goofiness. I had to distribute the 2 back in there. This piece, I'm going to go back and recap here in another video, but that's to get you to, we'll start with example 2 in the next spot. But hopefully that gets you started, something to try and see if you can piece that together. I think the cleaner version's here. Oh, here it is. Way better. Here's uv minus integral of v du. Got it. Sorry, I had to rewrite this because it was such a mess. And then the next piece is, if you, there's uv again, minus the integral of v du, you have to know the antiderivative of e to the 4x is 1/4 e to the 4x. Times an existent 1/4 makes that 1/16. This is our antiderivative. But without having known that the integral of e to the 4x is 1/4 e to the 4x, you might have gotten hung up on there. but very doable. So we're going to go to another example and see how it goes. Well, 2's got to go back in there as well. All right, let's get to one that's more doable.